All right, so with that, let's get started. And to start today, I want to talk about just the core elements of machine learning. And as we talk about these elements, I want to consider a motivating example throughout just to make all of the different concepts I present concrete. So in particular, imagine that we want to take an image of a face and predict whether that face is smiling or not. Now, I know predict sounds a little bit odd in this context. What we really mean is what would happen if a human were to look at this face? Would they say that it is smiling or not? And we want the machine to predict what that human response would be. So to approach this problem, the key idea in machine learning is to represent this label, whether they're smiling or not, using a model, a mathematical description of the data. A model, a mathematical description of the data. And so the first step in this process is to collect raw data. So what we need are a whole bunch of images representing different faces with different facial expressions, some smiling and some not smiling. So this would be e.g. photos of faces. Our second step is going to take this data and do preprocessing. And so in here, what we're doing is we are performing simple operations on the data that's not going to affect our end task, but will make the task easier. So we are going to change the data to make learning easier. And so, for example, in our facial recognition context, this could correspond to cropping the images. We might want to center the faces. We might want to make sure that each image has the same number of pixels. Perhaps there's some graininess to the images and we want to clean them up a bit. So you can see how these things, these operations, are not really going to affect whether or not the face is smiling or not, but they can make it easier to perform learning. So for instance, if the mouth is in the same part of the image in every single image, then that's just one less source of variation for us to worry about. So this is a very common task for most data sets. The third is feature extraction. This is a task that's central but which has evolved quite a bit over the history of machine learning. So what we mean by this is now we are going to reduce the raw data by representing it in terms of features or properties relevant to the task. So, for instance, in our facial recognition example, we have these images of faces that have eyes, eyebrows, a nose, and a mouth. And we want to make a prediction about whether this is smiling or not. In its raw form, this image is a list of pixel values. How much red and green and blue light is there at every single location in this image? Feature extraction might say, well, rather than dealing with raw pixel values, I'm going to measure certain things. Let's say the distance between the left eye corner and the left mouth corner, and the right eye corner and the right mouth corner, or maybe how wide the mouth is, or the distance between the ear and the mouth corner. So we might have a variety of different facial features that we can extract, and then instead of representing the image in terms of its pixel values, we represent it in terms of, say, these different distances between different facial features. This can be extremely helpful in settings where you might not have a whole lot of training images. So if I wanted to perform machine learning and all of my images have millions and millions of pixels, you could imagine that many aspects of that image are irrelevant to my task. The color of the background, the color of the hair, a variety of whether or not they have earrings, all of that's irrelevant to whether or not they're smiling. And if you have a small amount of training data, you run the risk of your model or your mathematical algorithm focusing on features that are just spurious correlations that have spurious correlations to the label or to the task that you have at hand. And so reducing the number of features from, say, millions of pixels to on the order of 10 or 20 different facial features can make you much more robust to those sorts of spurious correlations. Now, I said that this is something that's actually evolved in recent years. So there's a few different variants of this. What I've just described is, I guess I would say, manual feature selection. Where an expert decides which features are relevant. I'm using the word expert loosely here. When we look at some modern tasks, or modern methods like using neural networks, what we saw in the intro slides is that those models can actually perform well even when we don't have feature extraction steps, and we're just feeding in raw pixel values into the neural network. And we also saw that different layers in the neural network can be attuned to different feature images. And so in that context, we would say that in the process of learning to assign labels to the different images, we are also learning good features that are relevant to the task. So there is feature learning, which would happen, for instance, with a neural network. Now, to be clear, in order for this to happen, in order for us to have good feature learning, typically we need very large quantities of data. And in fact, that's one of the things that really was key to neural networks taking off, is the building of enormous data sets that these models could be trained on. So if you don't have enormous data sets, sometimes it is important to do this manual feature selection. But a third category that we see commonly is to have a foundation model. And this is something that we aren't going to talk about in any great depth in this class. But I just wanted to mention it in case you just hear it and people discussing it. And this refers to settings where people have taken enormous data sets and trained neural networks to do a variety of different kinds of tasks, and along the way perform feature learning. And then taking those learned features and using them as sort of in this context of manual feature selection. So instead of an expert coming along and saying, oh, you should look at the distance between the left eye corner and the left mouth corner, we would instead say, oh, my foundation model says, here is an important feature, so you should extract that feature from your images. And so these foundation models lead to somewhat generic features that can be used for a variety of tasks without expert knowledge, but also without requiring us to have so much data for our specific task that we are able to do feature learning on our own. Okay, so the next element is to generate training samples. Oh, and this is number 4. So we've collected all of these images. We've done our preprocessing, and we've done our feature extraction. And so now we are going to form training samples. And we are going to write this as pairs xi and yi for I equals 1 to n. So in this setting and with this notation, n is equal to the number of training samples. Yi is equal to the label of the ith sample. So for instance, this could be +1 if the image has a smile in it, and -1 otherwise. Next, we have our feature vector xi. So I'm writing it like this with the underline on it, under it. In the typed notes, this is going to have a bold font. And we do that to correspond to indicate that this is a vector. It's going to be a list of different feature values. So this could contain, for instance, the distance from the left eye to the mouth corner, the distance from the right eye to the mouth corner, and the width of the mouth. There we've got 3 different features, and we're putting them all together in this one vector, xi, and we use this underline to indicate that there could be more than one feature in this vector. So this is equal to the features of the ith sample. And in general, we are usually going to use the letter P to be the number of features per sample. Okay, so, and then a little bit more specifically, if I wanted to talk about the jth feature, one specific feature in this entire vector, I would write that as xij. So this is the jth feature of the ith sample. Now, I want to pause for a moment and mention that in this class, for the most part, we're going to assume that we're just handed data like I've written out here. And that somebody has already done the feature extraction, done whatever pre-processing, selected what photographs to include, and labeled them. Now, in real life, all of these steps involve a number of different decisions that are extremely important. And so just as an example, if you were to, from the outset, only have images from one ethnic or racial group, then you run the risk of developing a machine learning model that really is only accurate at predicting smiling for that racial or ethnic group. Or, as we talked about earlier, decisions about how we actually assign labels to images, what human expertise we get, or what kinds of algorithms we use to assign labels, those also can have downstream ramifications. So again, we're not going to be covering those decisions, in part because they really depend very much on the context in this class. But I just want to take a moment to emphasize how important it is to think through that. And if you have a job where someone hands you a data set, it's completely valid and often extremely important to ask, where did this data come from? What were the decisions that went into it? How was it originally intended to be used? How is that related to the task that you're being asked to use it in, etc.? Okay. Now, I also want to emphasize that we have, I'm kind of focusing on one aspect or one form of machine learning here, called supervised machine learning, and that is going to be our initial focus in this class. So when we talk about supervised machine learning, we mean that each sample has a label. And so when we talk about classification, what we mean is that the label is equal to a class indicator. So that could be whether or not someone is smiling, for instance. Or we could have more than one class. So we might have whether or not there's a dog in the image, whether or not there's a cat in the image, whether or not there's a face in the image. So we might have multiple different classes that we're considering. We might also have regression. And when we talk about regression, what we mean is that the label is a real number. So maybe what we want to do is predict someone's, say, height based on their shoe size. So that's not a category we're trying to predict. Rather, it's just a raw number indicating something that we care about. When we talk about unsupervised machine learning, we have unlabeled samples. So, for instance, when you think about generative models, those are trained with huge quantities of data samples, say images, and those images aren't necessarily labeled with anything indicating their content, they're just images. And so what we're trying to do is to learn how to generate new images based on the images we've already seen, and we can do that without labels. We also see things like semi-supervised learning, or there's self-supervised. And these are important concepts, but beyond the scope of what we'll cover in this class. But once you have the foundations that you learn in this class, you'll be able to take subsequent classes where you can learn about these things in more detail. But in this class, for the first part, we're going to focus on supervised machine learning. And then later in the quarter, we are going to move to unsupervised machine learning. We'll talk about dimensionality reduction, clustering, and a variety of other problems within this space. And just to be clear, when we talk about supervised versus unsupervised, The idea is that the label is somehow supervising how we perform learning. Okay, so with that in mind, we can now move on to the next step. We finally have our training data all set, and we actually want to do a little bit of learning. So to learn a model, we first have to choose a loss function. What the loss function is going to do is tell us how good or bad a model is. So for instance, let's just do a concrete example quickly. In our case of people smiling or not smiling, this could be, the loss could be the number of people misclassified. So it could be the number of people we say are smiling when they're not, or the number of people who we say are not smiling when they are. It turns out that this particular loss function is very hard to work with, and so in the coming weeks, we're going to talk about why that is and alternative loss functions that we can use. But this is just a quick example. And then finally, we are going to learn the model. So in general, what this means is that we search over a collection of candidate models and choose the one that has the smallest loss. And so in particular, and when I say loss, we're going to be looking at the loss on the training data. Okay, so let's make all of this very concrete with an example here. So I'm going to imagine that I have training data that corresponds to a variety of different samples with 2 features each. So I'm going to have X, and this I'm going to write : 1. So this means that it could be any of the samples I from 1 to n, but I'm looking at the first feature. And then over here, I'm going to have X : 2. So in our running example of classifying the features, or classifying whether someone is smiling or not based on facial features, this could be distance, eye to mouth. And this one could be mouth width. Okay. And then we can plot our training samples. And so we might have a whole bunch of examples where the person is not smiling. And so each one of these corresponds to a different eye. So this might be eye is equal to 1. That might be our first training sample. And so we're saying for the first training sample, it has this particular distance from the eye to the mouth, this particular mouth width, and the label associated with it, y1, is equal to -1. And then we also have our positive examples. And so what we're talking about here would be, for instance, a different one, maybe I is equal to 10 and y10 is equal to positive 1. Now, when we talk about families of models, we're thinking about, in this classification context, different ways we could draw a dividing line within this data. So let's imagine for initially that we're going to constrain ourselves to only having straight lines that tell us how to classify, like this. Okay, so this is one particular model. We could draw another model, for instance, like this. It's also a straight line. But if we were to measure our loss for these two different models, and we look and see how many errors are made by each model, we see they have very different values, right? This solid line is making 3 mistakes on this sample, and this sample, whereas the dashed line is making far more mistakes. So when we draw these lines, what we mean is that in the future, if we get a new sample and it lies below this line, then we are going to predict for that new sample that the label y hat is positive 1. And for any new sample that lies above this line, we are going to predict that the label y hat is equal to negative 1. And so on these samples, oops, this one was not a mistake, we only had 2. For these 2 samples here, this solid line is yielding a prediction that is different than the actual label that we had in our training data. And so our loss function is telling us how bad of a model this solid line is. And when we are doing our learning of the model, it means we're searching over all these candidate models. So in this case, say all different lines of different slopes and different intercepts, and choosing the one that minimizes our loss, in this case perhaps minimizing the number of errors we make on the training data. Another thing I want to quickly mention is that by controlling the complexity of the models, we can avoid problems like overfitting. So an alternative might have been that we have much more complicated models and end up with a decision boundary that gets 0 errors on the training data. Something like this. And so when you look at this, you might think, oh yeah, that looks better because this orange decision boundary has not made any mistakes. But what you run the risk of here is overfitting. That somehow, perhaps there's a few different errors in the training set. And so later on, you get a new sample here, which really should be, at test time after you've deployed your learned system, where it really is a photo of somebody not smiling. But because you were so carefully attuned to this one positive sample here and overfit to it, you're no longer able to make as good of predictions on new samples. And so we're going to talk more about this, how to prevent overfitting, later in the course. But before we get to that, I want to highlight sort of the final key element that we will be considering here. Which is to characterize the generalization error. Okay, so when we talk about characterizing the generalization error, we are talking about the average error of our predictor, say of our decision boundary, on new data. So estimate average error of the learned model on new data not used in training. So for instance, we could have a whole bunch of test samples. And the test data are generally assumed to be from the same distribution as our training data. So they would also have the form xi and yi. Maybe I'll just put a little superscript t here for test. So these are different samples, but they've got the same features. The labels mean the same things. And so what we can do is we can learn a model on our training data, and then after the fact, take our test data and evaluate how many times we make a mistake with our learned predictor on this test data. And this is telling us our generalization error. Okay. So now I want to dive in a little bit more to this classification example, talk more about a concept I introduced a little bit earlier, the notion of a vector, and also how we can start mathematically representing this notion of linear classifiers. Okay, so in our classification problem, we are going to, again, get samples xi, yi to train on from I equals 1 to n. And the yi's are going to correspond, in this case, to binary labels. So we write this as yi is in -1 or +1. So it means every single yi is either a plus or a -1. It's in that set. Or sometimes you see people use yi is equal to 0 or 1, just because it can be mathematically more convenient in certain settings. Our goal is to learn a model that accurately predicts the label for a new sample. So we're going to use y hat to correspond to the predicted label. And for a new feature vector, and I'm going to write this as x naught, just to be very clear that it is not one of our training samples. It's a new sample that we're going to get after training for which we want to make a prediction. Okay, so now when we do this, let's consider this notion of a linear model. And in particular, the idea is that our label, y hat, is going to be a weighted sum of the features. So we are going to have x01, x02, x03, all the way out to x0p, where p is the number of different features. And like I said, we're going to use a weighted sum. So we're going to have w1 times x01 plus w2 times x02 plus w3 times x03, all the way out to wp times x0p. So with this linear model, we know that we are going to get these kinds of straight line decision boundaries or linear decision boundaries. And in particular, the weights are going to be what we learn from training data. So when I talk about over here, trying to choose between the dashed line and the solid line, what I mean is we are going to try to choose the best set of weights within the context of this linear model. Now, when we write out this weighted sum, it can be a little bit cumbersome. And so we're going to introduce some notation that's going to simplify a lot of things for us a little bit when we first start talking about linear models, but a huge amount as we progress further and further into the course. So in particular, we are going to let W, or maybe I'll just use my orange again here, W with the underline be our weight vector. So we have in this vector W1, W2, W3, all the way down to WP. And I'm going to write this as in, and then sort of a bold blackboard R to the P. And what this means is that this weight vector W has P different entries, and each one of them is a real number. And we are going to call this a weight vector. And similarly, we are going to have x naught vector be written as x naught 1, x naught 2, all the way to x naught p. And it also is in Rp. It is a vector of p different real numbers. And so now, armed with this notation, we can express this linear model with some shorthand. And in particular, we can write this as an inner product. So we can write the inner product in a few different ways. We could write it as x naught comma w inside these angle brackets. And that's the same as w inner product with x naught. So in this inner product, the order doesn't matter at all. And we can also write it as x naught transpose w, or w transpose x naught. And this notion of transpose is very simple. I'll just map it out over here. So when we talk about a vector, let's say W transpose, we indicate it with this superscript that looks like a little t. And it means that we are going to have W1, W2, all the way to WP, all in a row. And so when we talk about W transpose x naught, then this means W1, W2, all the way to WP times x naught 1, x naught 2, all the way down to x naught p. And so what's happening here with this notation is we're saying you're going to multiply the first elements of the two vectors, the second elements of the two vectors, all the way to the pth elements of the two vectors, and then add up all those products, which gives you exactly the weighted sum of our linear model. Okay, so now we've set the stage, and next time we're going to talk more about how we can use this notion of a vector and additional notions related to matrices to formulate our learning problem and start learning weights from data. Thanks very much.